Hi everyone, my name is Juan López Salazar. I'm a student at the Universidad Nacional, Abierta, Distancia, and today we're going to check the phase 3 of the Videogames optimization course. In this phase 3, we're going to implement two optimizations to the video game that I reviewed the last phase, phase 2, with the Unity profiler. So, these two optimizations are called baked lighting and static batching. So, let's see how we can do this inside Unity. Let's go. Okay, so this is the game. It doesn't contain any optimization yet. It's just to show you that it runs pretty smoothly, and we can see here the FPS. But also we're gonna check a little bit of the profiler here. Well, you can see it has a lot of spikes and a lot of stuff going on, and we're gonna solve that real quick with this first optimization. Let's start with the static batching. This technique allows Unity to combine multiple static objects that share the same material into larger meshes, so they can be rendered with few draw calls. Each draw call requires the CPU to tell the GPU what to draw, so reducing them helps improve performance. To apply it, I select all the objects that don't move in my scene and mark them as batching static in the inspector. Unity then pre-combines these meshes to render them more efficiently. Static batching slightly increases memory usage because Unity duplicates geometry internally, but it gently reduces CPU overheat in larger scenes. In my case, the performance difference is minimal since my computer is very powerful and the project is real small. But this process prepares the game for scalability and smoother performance on weaker devices. So yes, this is static batching. The second optimization is light baking. In Unity, real-time lighting continuously calculates shadows and light interactions, which is expensive for the CPU and GPU. Light baking pre-computes that information and stores it in light maps, so the game only needs to read those textures instead of recalculating lighting every frame. I set my lights to baked mode and enabled baked global illumination in the lighting window. This greatly reduces the workload of real-time lighting and produces smoother shadows and reflections with almost no CPU cost during the gameplay. So the lighting is now completely static, which stabilizes the frame rate and removes unnecessary light computations. This process can take long, so be patient, but I told you it's completely worth it. The third technique is occlusion culling. Normally, Unity renders all objects within the camera view, even those hiding behind walls or other geometry. Occlusion culling prevents that by skipping objects that camera can't see. I marked large walls and buildings as occluders and small props as occludes, then baked the occlusion data. This allows Unity to avoid sending hidden objects to the GPU, reducing rendering load when moving around the scene. In small projects like this one, the FPS gain is almost unnoticeable, but in larger environments, it can dramatically improve performance. It's an essential optimization for keeping rendering efficient and avoiding wasted resources. After applying these optimizations, the Unity profilers show a much smoother CPU usage graph with no spikes in global illumination, meaning that the lighting workload was successfully baked. Rendering became more stable too, and even though the FPS slightly decreased from around 447 to 411, that's normal on powerful hardware like mine. The difference lies in consistency and efficiency, not raw frame rate. These optimizations make the project more predictable and scalable. They reduce unnecessary real-time calculations and improve how Unity handles rendering internally, ensuring better performance on lower-end systems and larger future scenes. So yeah, this is it. Thank you for watching this video, and I hope it helps to everyone. Bye!